In this video, we're going to work some example problems related to how derivatives affect the shape of a graph. This isn't curve sketching yet. Curve sketching is coming up next. But what we learned about in this section and just in the opening sections of this chapter is how we can use the first and second derivative to recognize things like, is a function increasing or decreasing or concave up or concave down, and how we could potentially take advantage of the first and second derivative to check to see if we have a local maximum or a local minimum or an inflection point. And so the example problems we're going to work in this video are going to really, we're not going to do any curve sketching yet. There are some problems in this section where they ask you to do curve sketching, but to me, that's getting ahead. We're going to do all curve sketching in the next section. The problems we're going to work in this video is just going to be related to making sure you understand conceptually what we've learned so far about local maxes and mins, inflection points, the function increasing over an interval, decreasing, etc. And it's really important that you absorb and fully understand these concepts before you get into curve sketching. And so in addition to these example problems, I'm also I'm going to make a video next that's going to review everything we've learned so far in the first few sections, kind of summarize it all and bring it all together. And then from there, we can get into curve sketching. All right, let's get started. Okay, so one thing that we learned in this section, section 4.3, we learned how we can use the first and second derivatives to see if a function is increasing, decreasing, or concave upward or concave downward over an interval. So for this function, what are the intervals on which f is increasing? The open intervals, it says. So it's increasing from, and it's saying open intervals because so it's increasing from 1 to 3. But technically it's not increasing at 1 or at 3, right? So, but on the open interval from 1 to 3, it's increasing. And then on the open interval from, let's see, 2, 3, from 4 to 6, it's increasing. Which means that on these intervals, the first derivative of this function would be greater than 0. And that's what that's saying is that you pick any point and then you move a distance in the positive x, any distance in the positive x from that point without leaving the interval, and then evaluate the function at that distance, that increased distance x. Then the function, if you call the increased distance, if you call the first point x1 and the increased distance x2, then f of x2 is going to be greater than f of x1. That's what an increasing function means. It's the same idea with decreasing. Okay, so what intervals is the function decreasing? From 0 to 1, and then from 3 to 4. All right, now concavity, this is the second derivative. Concave up, you can think about, with concave up, you can draw a U. Up. A U for up. Concave down, it's the opposite. And so one thing to notice is that with concave up or down, a function can be decreasing or increasing and be concave up. It's increasing here, it's decreasing here, it's concave up both. Same idea here. A function can be increasing or decreasing and be concave down. All right, so where is it concave up? Well, it's concave up all through here. And then boom, it stops here. And then it switches to concave down. And then it switches here to concave up. You see? Right, you draw this U. You can't draw an upwards facing U when the curve's going in this direction. But it doesn't ever switch. Here, there's no switch to up, you see? It stays going in that upside down U direction. And then just at this point, it switches. You see the difference? Here, it doesn't, if it was concave up, it would continue concave up. Here, it switches to concave down. And then it could switch to concave up, but it doesn't. Here, it just continues concave down, see? And then here, it switches to, oh, wait, no, it doesn't switch to concave up. It stays concave down. Here, it's concave down. It could switch to concave up here. It could do, but it doesn't. So, you've got concave up from 0 to 3. No, that's not right. From 0 to 2. From 0 to 2, it's concave up, and then it's concave down the rest of the way. From 2 to 6. Well, no. Okay, it's concave up from 0 to 2, and that's it. And then it's concave down from 2 to 6. So concave up from 0 to 2, concave down 2 to 6. All right, now the coordinates of the points of inflection. What is an inflection point? Well, it's kind of similar to a local max or min. This, at least similar in the sense of how you test for it, right? It's not actually similar to a local max or min, but it's similar in the way you test for it. But there are, I don't want to, that's not an official statement because there are some differences. Number one, the main difference is that an inflection point we saw is that the curve has to be continuous there. However, we did see you could have a local max or min at a discontinuity, but there's no inflection point at a discontinuity. So, well, the curve is continuous everywhere in this interval. Now, okay, so it has to be continuous. Okay, now what else? What does it mean to have a point of inflection? It's any point where the curve changes from concave down to concave up or vice versa, or where the second derivative changes sign. That's it. So there's only one point where it changes sign. Here, we saw that. When we go from 0 to 2, then from 2 to 6, so at this point, at 2, 1, 2, 3. That's the only point of inflection. It could change here. This would be if the curve did this, instead of this would be an inflection point. But it doesn't change sign, so it stays concave down, so it's not. The graph of the derivative f prime of a function f is shown. On what intervals is f increasing or decreasing? All right, this is the graph of the derivative, okay? Not the function itself, all right? So the first question is, on what intervals is f increasing or decreasing? This is easy. This is like, it's so easy, it makes you if you don't know this well, it's so easy you think it can't be that easy. If the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. That's it. So anywhere below the x-axis, the function is decreasing. Anywhere above, it's increasing. That's it. And we're going to say open intervals because it is technically not increasing or decreasing when it's at the x-intercepts. So increasing on the interval from 0 to 1, and then from 5 to 7. Decreasing on the interval from 1 to 5, and from 7 to 8. They're trying to confuse you with all this waviness here. This must mean something, right? They drew all this detail. It has to mean something. Doesn't mean anything. At what values of x does f have a local max or min? Oh, well, right here, here's two local mins. And here's a local max. Wrong. This is the derivative. You have to think about what are the properties that, if you're trying to find a local max or min, what are the conditions? Well, if there's going to be a local max or min, it's going to be at a critical number of the function, 100%. What does a critical number mean? Now, it's not that every critical number is a local max or min, not necessarily, but if there is a local max or min, it's going to be a critical number. What does a critical number mean? A critical number of a function is where the derivative is equal to 0 or where the derivative doesn't exist. Well, in this interval, there's no points where the derivative doesn't exist. So the only potential points where there's a local max or min is where the derivative is equal to 0. So there's 3 possibilities. Okay, so that's it. At x is equal to 1, 5, and 7. No, not done yet. Just because the derivative is equal to 0 at a point doesn't mean it's necessarily a local max or min. How do you test to see if you have a local max or min? There's 2 ways to test. The first derivative test or the second derivative test. We don't have any information about the second derivative. So what's the first derivative test? The first derivative test is, first of all, the function has to be continuous. at least over the area, the region that you're analyzing. So you can't apply this test at a discontinuity. Well, this is continuous, so we're fine. Well, the first derivative is continuous, so the function's going to be continuous as well. Okay, now, so the test is, all right, if it's a continuous function and you have a critical number, we have 3 critical numbers, does the first derivative change sign across that critical number? Well, it does at all 3 points here. And so now, all right, so we have 3 local maxes or mins. Now, which is which? Local max, local min. If the derivative goes from positive to negative, it's a local max, right? Because you go from increasing to decreasing. So x is equal to 1. And we also go from positive to negative here, so x is equal to 7. If it goes from negative to positive, then it's a local min, right? Negative slope to positive slope, local min. In each part, state the x-coordinates of the inflection points of f. Give reasons for your answers. So for part A, this represents the function. For part B, it represents the first derivative. And part C, it represents the second derivative. Okay, so what are the inflection points? What does inflection point mean? It has to be, the function has to be continuous. And so, okay, part A, the function is continuous, so that's not a problem. And then it's where the second derivative changes from positive to negative or negative to positive. So if we're looking at the function, then how can we check the second derivative? We look for concavity. Here we're concave down, concave down, concave down, concave down, concave down, boom. We switch to concave up here. Concave up, concave down, boom, we switch to concave down. So the x-coordinates of the inflection points are going to be x is equal to 3 and x is equal to 5. All right, now if this is f prime, okay, now in this case, then the derivative of this function is f double prime. So, in other words, the curve is, we're analyzing again. We're trying to think about the second derivative, but if this is f prime, then where the slope is positive, the curve is concave up. And where the slope is negative, the curve is concave down. So concave up, concave up, concave up, concave up. Now we switch to concave down. Concave down, concave down. Now we switch to concave up. Concave up, concave up. Now we switch to concave down. You see? So the inflection points are x is equal to 2, x is equal to 4, and x is equal to 6. All right, now if the graph is f double prime, well then it's concave down if you're below the x-axis, it's concave up if you're above. So okay, the second derivative is 0 here, but you don't switch. You don't switch signs. So 4 is not an inflection point. X is equal to 1 is an inflection point, and x is equal to 7. That's where you switch signs. The graph of the first derivative f prime of a function f is shown. On what intervals is f increasing? All right, so this is the first derivative. Okay, this is f prime of x. So in what intervals is f increasing? Increasing, that's easy. Again, they're putting all this waviness to confuse you. Above the x-axis, the first derivative is positive, it's increasing. Below the x-axis, the first derivative is negative, it's decreasing. That's it. So A, it's increasing from 0 to 4, and then from 6 to 8, this is increasing, and then it's decreasing from 4 to 6, and 8 to infinity. Right? That's what the first derivative means. The first derivative is giving you the slope of the tangent line of the curve at a point. If that slope is positive, it's increasing. At what values of x does f have a local maximum or minimum? A local max or min. So the function doesn't have to be continuous when it comes to local maxes and mins. but to apply the first derivative test, it does. And so it looks like we're going to need to apply the first derivative test, and this is going to be a continuous function. If the derivative is continuous, then the function is going to be continuous. Okay, so we have a continuous function. What are the critical numbers? Well, there's no points where the first derivative doesn't exist. There's 2 points where the first derivative is equal to 0. Okay, so those are the only 2 potential spots where you have a local max or min. Now let's apply the first derivative test. Does the first derivative change signs across those points? Yes. So we go from positive to negative. So local max at x is equal to 4, and then a local min at x is equal to 6. You go from negative to positive. On what intervals is f concave upward or concave downward? Okay, this is a little confusing, but we've got the first derivative here. So the second derivative, which is what we're trying to analyze, because we're analyzing for concavity, that's the first derivative of this function here. Okay, so what we're looking for to analyze the concavity, we're looking for where is the second derivative positive or negative. If the second derivative is positive, it's concave up. If it's negative, it's concave down. So what can we get from this function here? What we're trying to analyze the second derivative, that's the derivative, the first derivative of this function here. If we want to see where the first derivative of this function is positive or negative, we look for the slope. So from here to here, it's positive, concave up. Now the slope it's decreasing, so it must be concave down, concave up, concave down, concave up, concave down. Okay, so concave up will be from 0 to 1, 2 to 3, 5 to 7, and that's it. And then concave down will be from 1 to 2, 3 to 5, and then 7 to infinity. What are the x coordinates of the inflection points of f? Okay, so it just has the function for what is an inflection point? The function has to be continuous at that point. You can't have a discontinuity. That's not an issue here. So then you just check: if it's continuous, is there a change in sign, or is it you go from concave up to concave down at a point? That's an inflection point. Well, look, we just did this. So you switch from concave up to concave down. It was here, 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 and here. So those are the inflection points. X is equal to 1, 2, 3, 5, 7. There's 5 inflection points. All right, we're given a function. Find the intervals on which f is increasing or decreasing. Okay, how do you do this? How would you think about, if you were given a function, how would you find the intervals where the function is increasing or decreasing? Well, okay, the idea is you want to find what intervals is the first derivative greater than 0 and what intervals is it less than 0. Well, there's only one, the function can change signs. The function can switch from a derivative greater than 0 to less than 0 only at a critical point. It has to be a critical point. If it's not a critical point, then there can be no change in sign. And I'll leave it to you to think about why that's the case. A critical point, it could be a discontinuity. It could be a continuous point, but where the first derivative doesn't exist, like this. Or the first derivative does exist and it's equal to 0 at that point. If it's not a critical point, one of those scenarios, then the function can't switch sign. The first derivative can't switch signs. Okay, so step 1, find the critical points. And you can imagine if you wanted to find the intervals, we're going to find the intervals of concavity. You're going to need, it's going to start with the same process of finding the critical points. So let's find the critical points. How do you find the critical points? Well, you want to find the points where the first derivative is either equal to 0 or doesn't exist. Okay, so we need to start by taking the first derivative. Okay, there's no x where this doesn't exist. This is a polynomial. The domain is all real numbers. So the only possible critical points are where this is equal to 0. All right. Now let's solve this. Factor out a 3. So divide both sides by 3. Wait, this is not right. Okay, so let's factor this. All right, we got a 3 and a 1, and then minus 3. There we go. So x is equal to 3, and x is equal to minus 1 are the critical points. Okay, so now what do we do? Well, we know that these are the only potential points where this function, the first derivative, can change signs is at these two points. These are only spots. So all we do is just check. Okay, when x is less than 3, what is the function? Is the function positive or negative? When x is greater than 3, is it positive or negative? You just check all around these points. So, in other words, if we've got a number line here, so 1, 2, 3. 1, so minus 1, 3. Just check these 3 regions here. You see? Okay, so just let's plug in for this region here. Let's plug in the simplest number in this region. You can't plug in minus 1 because it's the first derivative is going to be equal to 0. You have to plug in something off of the critical point. So let's do so f prime. We're checking to see where the first derivative, to answer this question, we need to see where the first derivative is positive and negative. Okay, so minus 2 squared is 4. 4 times 3 is 12. Minus 6 times minus 2 is positive 12. So 15. So it's positive here. So this is going to be it's going to be increasing in this region. From negative infinity to minus 1, the open interval, the function is increasing. Okay, so it must be decreasing here then. No. You can absolutely have a critical point that's not, but it could bounce off, like it could go to 0, then it could do this. Now the slope is 0 and it continues positive. So you need to check. F prime, it probably is going to switch, but just check. Plug in the simplest number in that interval, so 0, minus 9. It did switch, so now it's decreasing. Right? You see the intervals? Okay, now you got to check again. You have to check. You can't just assume it's going to go to increasing, so f prime of 4 is 4 squared is 16. 16 times 3 is 48. 6 times 4 is 24. 24 minus 9, 15. Look, it didn't switch. Or no, it did switch. I'm sorry. Yeah, it switched. Yeah, it's the same as the first interval. Okay, so there's the intervals where the function is increasing and decreasing. From minus infinity to minus 1, the function is increasing. That means the first derivative is positive. From minus 1 to 3, the function is decreasing. The first derivative is negative. And then from 3 to infinity, increasing. The first derivative is positive. But you would put open intervals because it's at these not inflection points, these critical points, it's not increasing or decreasing, right? The first derivative is equal to 0. All right. Now the local maximum and minimum values of the function. All right. The function doesn't have to be continuous to have a local max or min. For an inflection point, it does. But it doesn't matter anyway because there's no critical points where the derivative doesn't exist. The first derivative doesn't exist. Okay. So in that case, but you do need continuity to apply the first derivative test to check for a local max or min. Okay, so it's continuous. What's the first derivative test? At a critical point, does the first derivative change signs? then it's a local max or min. So a local max, and there's going to be a local min. Okay, we go from increasing to decreasing, increasing to decreasing. X is equal to -1 is a local max. Then from decreasing to increasing, X is equal to 3 is a local min. All right, the intervals of concavity and the inflection points. Okay, same process for the intervals of concavity. We need to find the second derivative. All right, so 6x minus 6. And then in a similar way, you would see where does the second derivative not exist and where is it equal to 0. It's a similar idea as far as you could have the second derivative not exist and have an inflection point. They don't call it critical numbers when it comes to the second derivative, but it's the same idea. That there is a difference in that at a discontinuity, you can't have an inflection point, but at a discontinuity, you can have a local max or min. It's kind of like the way they present it in the book. It's kind of like local maxes and mins are parallels to inflection points. It's kind of like that. It's like they teach it kind of the same way, but you can have a local min at a discontinuity. You can't have an inflection point at a discontinuity though. Okay, so the second derivative, there's nowhere where it doesn't exist. Let's just solve for where this is equal to 0 and x is equal to 1. So the similar idea in that you only where the second derivative is equal to 0 or doesn't exist is there a possibility for the second derivative to change signs. So if we're first trying to find the intervals of concavity, you want to find first where are the only possible points where the second derivative could change signs. It's similar to the critical numbers. It's where the second derivative doesn't exist or where it's equal to 0. It could change signs at a discontinuity, the second derivative. That's a potential, right? You could do just like here. We went from concave down to concave up. This is just not called an inflection point is all. But you would still, this is how you would still analyze for the intervals of concavity. This would be where the second derivative doesn't exist, one of the points. So that would be where you could potentially change signs. Okay, we only have one point where the second derivative could change signs at x is equal to 1. So just plug in to the left and right. So to see the second derivative, so the sign of it. So f double prime of 0 is equal to -6. Okay, so it's concave down. There's nowhere, it can't change anywhere out here. It has to stay concave down. Anywhere where it's less than 1. Because how's it going to change signs? There's no discontinuities. There's no points where the second derivative doesn't exist. There's no points where the second derivative is equal to 0 when x is less than 1. So it has to be concave down everywhere. All right, now what about greater than 1? Does it stay concave down? Let's plug in 2. 6 times 2 is 12. 12 minus 6 is 6. No, it goes to concave up. Okay? So from minus infinity to 1, it's concave down. From 1 to infinity, it's concave up. All right? What about inflection points? Well, the curve is, there's no points where the second derivative doesn't exist. That would be the only point where you could potentially have a discontinuity. You could still have a continuous function and have the second derivative not exist. But if it's going to be a discontinuity, then it has to be where the second derivative is not going to exist. Second derivative exists everywhere, so at this x is equal to 1, we just check to see, is there a change of sign? If there is, then that's an inflection point. So x is equal to 1 is an inflection point. Now, you might say, well, oh, don't we need to see what direction it went? From negative to positive or positive to negative? Not with inflection points. It's not like a local max or min depending on if you go from positive to negative or negative to positive. No, with inflection points, it's just a change of sign. That's it. Any direction. Okay, same question. What intervals is the function increasing or decreasing? Let's find the critical numbers. Okay, f prime is cosine of x minus sine of x. And we're only analyzing it from 0 to 2 pi. Okay, Is there anywhere where the first derivative doesn't exist? No. What about if we set this equal to 0? So sine of x is equal to cosine of x. Divide both sides by sine of x. So you get cotangent of x is equal to 1. So x is equal to inverse cotangent of 1. Okay? So inverse cotangent, we're in radians. You want to be, remember, when you're dealing with derivatives of trig functions, you need to be in radians. Well, you don't have to be, but that's what, if we're going to say that, like if we took these derivatives here, like when I took the first derivative, I was assuming we were in radians, or else I would have to do this differently. I would have like factors out front, like something over 360 or 1 over 360 or something like that out front. So once I took the derivative this way, saying sine of x, the derivative of sine of x is cosine of x, and the derivative of cosine of x is minus sine of x, then I was assuming that we were in radians. So we need to be in radians. Pi over 4. Okay, so that is the only spot where this function could change signs. The first derivative could change signs. So we've got pi over 4. Okay. Let's plug in f prime of 0. Okay. Cosine of 0 is 1. Sine of 0 is 0. So this is positive. So the function is increasing in this interval. All right. What about f prime of, so pi over 4 is less than 1. So let's just put in, well, we're not going to put in 1. Let's put in something, what about pi over 2? That's greater than pi over 4. Okay, so, well, actually, let's just do pi. Yeah, that's even easier. So what is, yeah, cosine of pi is what? Think about the unit circle. Cosine of pi is minus 1. Sine of pi is 0. So decreasing. All right, so from negative infinity to pi over 4, the function is increasing. From pi over 4 to infinity, it's decreasing. All right, and so the local maxes and mins, you're going to have a, so you go from increasing to decreasing. This is going to be a local max. So at x is equal to pi over 4 is a local max, and that's it. Okay, now the intervals of concavity, let's take the second derivative, so minus sine of x minus cosine of x. Okay, there's no points where this doesn't exist. All right, so minus sine of x is equal to cosine of x. And then, so minus cotangent of x is equal to, well, cotangent of x is equal to minus 1. Which means that x is equal to the inverse cotangent of minus 1. Three pi over 4. Okay. So this is 0, 3 pi over 4. Okay, when now f double prime of 0 is what? Minus sine of 0 is 0, minus cosine of 0 is, so this would be minus 1. So we've got decreasing, or no, not decreasing, concave down in this interval. All right, now what about above? We need to check. It's probably going to be concave up, but you should check. So 3 pi is like 3 times 3 is 9, so 9/4. Well, no. Okay, no, we just do this. of pi. That's greater than 3 pi over 4. So minus sine of pi is 0, minus cosine of pi is, so cosine of pi is minus 1 with a minus, so there you go, concave up. And this is going to be an inflection point. It's continuous, everything we've talked about. So the intervals of concavity, it's concave down from minus infinity to 3 pi over 4, and it's concave up from 3 pi over 4 to infinity. An inflection point is, a change of sign in concavity is at 3 pi over 4. X is equal to 3 pi over 4. Okay, last problem. Same question, different function. So what are the intervals where the function is increasing or decreasing? Find the first derivative. Okay, but now we've got a critical point where x is equal to 0. That's where the derivative doesn't exist. Okay, so critical points. One is x is equal to 0. Another would be, we need to solve this for when, where's the first derivative equal 0? Okay, so let's multiply this by x. So you've got 2x squared minus x minus 1 is equal to 0. Okay, so we need to, can we factor this? So 2 times minus 1 is minus 2. So minus 2 plus 1 is minus 1. Okay, so we could do 2x squared minus 2x plus x minus 1. That hasn't changed the equation, so now let's factor out a 2x here, and you get x minus 1, and then here you've got x minus 1. So now we can factor out an x minus 1. Okay, so 2x plus 1 is equal to 0, x is equal to minus 1/2, x minus 1 is equal to 0, x is equal to 1. So x is equal to minus 1/2, and x is equal to 1. Those are the 3 critical points. What does that mean? That means that these are the only possible points where the first derivative could change signs. So all we need to do is draw a number line to find the intervals in which f is increasing or decreasing. Draw a number line and put these points. So here's 1, minus 1. Okay, so there's minus 1/2, and there's 1, and there's 0. So that's the intervals. Now just plug into the first derivative a point in this interval, 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 and then you just mark it off. If it's positive, put increasing. If it's negative, put decreasing. So f prime of the simplest number we can that's not minus 1, on the left side of minus 1 would be minus 2. So minus 4, minus 1, and then plus 1/2. Minus 1 plus 1/2 is minus 1/2. Minus 8/8 minus 1/2 minus 9/2. So decreasing in this interval. Okay, what about this interval? So let's put minus 1/4. Two times minus 1/4 is minus 1/2. Okay. Increasing. It's positive. Okay, now let's plug in 1/2. Okay, so 1 minus 1 minus 2. Minus 2. Decreasing. Now let's plug in 2. Positive 2. Okay. F prime of positive 2, 4 minus 1 minus 1 half, 3 minus 1 half, 5 halves, increasing. Okay, so that's the intervals on which the function is increasing or decreasing. All right. Now, local maxes and mins. This is a little trickier this time, at least when it comes to the critical point where the first derivative doesn't exist. And it didn't, just to note, it didn't give us any interval here to consider on this function, but we can look and see what's the domain of the function. What's the domain of this function? The domain is x is greater than 0. I mean, that's kind of implied. If you're asked a question like this and just given a function, then it's implying that, okay, if it doesn't give you an interval, then it's saying over the entire domain of the function. So you can't input anything that's any x that's less than or equal to 0. Everything else is fine. And so with that, technically then, this is actually not a critical point. And what do I mean by that? Well, we've analyzed the way we've been going about it is, you know, we've been given, like, in general, we've been given like an interval, an open interval or closed interval, whatever, and we're analyzing it that way. We don't consider the endpoints when it comes to like local maxes and mins or critical points. We don't consider the endpoints, right? The endpoint is not a critical point. You see what I mean? You remember that? Endpoints are not critical points. This is an endpoint. X is equal to 0 is an endpoint, right? You think about the natural log of x. It's the graph of the natural log of x. It's like this. That's x is equal to 0 is not a critical point. It's outside of the domain. The derivative doesn't, for the natural log of x, the derivative doesn't exist all over the place in here. The entire, for x is the entire negative domain, that's not all critical points. No. So in that case, this is not a critical point. So we're going to have a continuous function over the entire domain. There's no x that you can input here, and the function doesn't exist as long as x is greater than 0. So it's continuous over the entire domain. In that case, we can use the first derivative test to see what if these two critical points, to see whether or not those are local maxes or mins. What's the first derivative test? You see, well, let me erase this. Well, okay, hold up. Yeah, and I messed this up. Okay, so this is outside of the domain. All this. There's only, okay, no, this is not a critical point either. This is not a critical point either because it's outside the domain. So I didn't explain that clearly, but you see what I'm saying? We should have identified the domain first of the function. So with that, there's only one critical point at x is equal to 1. And the function from its endpoint to the first critical point, it's decreasing. And then from the first critical point to infinity, it's increasing. This is outside of the domain. Okay, so we've got but it's continuous over the domain. So we can apply the first derivative test to the critical point. Does the first derivative change signs across this point? Yeah, it does. It goes from decreasing to increasing. It goes from decreasing to increasing. So this is a local min. X is equal to 1 is a local min. And here's the intervals in which the function is decreasing and increasing. All right, intervals of concavity. All right, the second derivative is 2 plus 1 over x squared. So x is equal to 0. This doesn't exist, but that's an end point. That's the only point where this doesn't exist. So what about where this is equal to 0? Well, there's no point. You can't take the square root of a negative number. There's no point where the second derivative equals 0. Okay, so with that, there's no point within the domain where the second derivative doesn't exist or where it equals 0, so it can't change signs. And that kind of makes sense because think about the natural log of x. It's always concave down. Okay, so, but how do we find out? So it's going to be the concave up or down over the entire domain, but which one? All right, well, we plug in f double prime of anything greater than 0. We can use this point here. This isn't the critical point is not that doesn't have anything to do with the second derivative. So we can plug this 1 in. You get 2 plus 1 is equal to 3. So it's just concave up. Concave up. And there's no inflection points. There's no change in sign from concave up to concave down.